Hello and welcome back to Math 3322. I'm Dr. Heath, and we are going to be going through section 2.2 of our textbook today. I have posted these slides on our Canvas page, but you'll notice that I've skipped over a few of them in this video just to try to keep it shorter. But you can see all of those slides on Canvas if you want to go and see the ones that I've hidden from this slideshow. All right, so this section is all about describing sets. So throughout this section, you should learn language and structure of sets as applied to elementary mathematics, connections between finite sets and whole numbers, and uses of one-to-one correspondence. All right, so way back in the 1800s, Georg Cantor created set theory, which has a profound effect on research and mathematical teaching. Sets and the relations between sets are a basis of teaching children the concept of a whole number, as well as the concept of less than, addition, subtraction, multiplication of whole numbers. So the language of sets, we have a set is any group or collection of objects. So I could have the set of all the students enrolled in this section. I could have a set of the pencils in my drawer. I could have the set of all even numbers. I could have the set of all of the numbers between natural numbers between 5 and 10. So these are any collection or group of objects. The objects that belong to a set are elements or members of the set. And we can denote a set using just curly brackets, and sets are usually labeled with a capital letter. So this set would be read as the set A is the elements 1, 2, 3, 4, 5. So each element of a set is only listed once, and the order of the elements is unimportant. So this example here, 1, 2, 3, 4, 5, the same set A could be written 5, 4, 3, 2, 1. We symbolize that an element belongs to a set using this symbol. It looks kind of like a squishy, soft E. And we use that same symbol with a slash through it to indicate that an element does not belong to a set. And then sets must be well defined, meaning that we have to be able to tell whether or not an object belongs to a set. So something like the set of basketball players who are tall would not be well defined because tall is subjective. So we don't have a clear definition of what tall means, but we could have the set of all basketball players above 6'5", and that would be a well-defined set because we could actually find their height and decide if they were classified to that set or not. All right, so we have a few different ways to describe sets. The first is just a listing out of the elements of the set. So this is what's also known as the roster method. So C is the set of the colors red, green, yellow, blue. So that's a finite set, just with 4 things in it. And then 2 important sets that we're going to discuss throughout this course are the natural numbers and the whole numbers. So the natural numbers begin with 1. They're like our counting numbers. So 1, 2, 3, 4, ... The whole numbers, however, start at 0 instead of at 1. And I always remember the whole numbers start at 0 because I think of whole, like a hole, and holes are round. So you start with 0, a round number. Or you can see that whole has a O in the number or in the letters of that word. So you start with 0, 1, 2, 3, etc. And then we also have other sets like the sets of lowercase letters. And again, in all 3 of these letter sets, the ellipses or ... dots tell us that the set continues in the same manner. We also have what's called set builder notation. So this is where instead of just simply listing out the elements of the set, we're going to describe the set in some more methodological way. So if we have C as the set, we would read this as set C is all elements X. This bar reads such that X is an element of the set of natural numbers, or X is in N, where N is the set of natural numbers, and X is less than 5. So if we think about numbers that would qualify here, we want all the natural numbers that are less than 5. So the natural numbers start at 1. So 1 would be an element of this set, 2, 3, 4. But then when we get to 5 is a natural number, but 5 is not less than 5. So this set would just be 1, 2, 3, 4. So if we try to take these sets and write them as set builder notation, we can do that using, these are arithmetic sequences. So the first example is 2, 4, 6, 8, 10. So we could say that this is X such that X is an even natural number, or we could write it more algebraically, saying X such that X equals 2n, where n is a natural number. So we can write any even number as 2n for n a natural number. So like 2 would be 2 times 1. 4 would be 2 times 2. And then B is the set 1, 3, 5, 7, continuing in the same way. So these are our odd natural numbers. So we can write that as X such that X is an odd natural number, or we can write odd natural numbers as X equals 2n minus 1. So we're just going to take all of those even numbers that we wrote about in 2n and subtract 1 from it. So 2 times 1 minus 1 is 2 minus 1, or 1. So we get that first odd natural number. We could also take set builder notation and write it in using the roster method and list its elements out. So this set is the set of 2k plus 1, where k is equal to 3, 4, and 5. So the easiest way to do this is probably just to create a table and say, all right, when k is 3, 4, and 5, I'm going to have the elements 2k plus 1. So 2 times 3 plus 1 is 7. 2 times 4 plus 1 is 9. 2 times 5 plus 1 is 11. So C is the set of 7, 9, and 11. All right, and we have another example here where set B is X such that X is a positive even natural number less than 8. So positive even natural numbers. So natural numbers are actually all positive because we start at 1, but we have the even numbers, natural numbers less than 8. So 2, 4, 6, and then 8 would not be included because 8 is not less than 8. So B is 2, 4, 6. Now, two sets are equal if and only if they contain the same elements. So in these sets, the order doesn't make a difference. So the set ABC is equal to the set CBA or BAC. Those sets are all equal, even though they're ordered differently. The order doesn't matter. If the sets are equal, then we just write A equals B for the two sets. And then we have this kind of nice way to think about set equality. If A is equal to B, then every element of the set A is contained in the set B, and every element of set B is contained in set A. And if they're not equal sets, then there's at least one element that's not contained in both sets A and B. So there would be something in A that's not in B, or something in B that's not in A. So different from set equality is a quality between two sets called one-to-one correspondence. So if the elements of two sets, P and S, can be paired so that every element of P has exactly one element of S, and for every element of S, there's exactly one element of P, then those two sets are called to be in a one-to-one correspondence. So, for example, set 1, 2, 3 can be placed in a one-to-one correspondence with the set A, B, C by either of these two ways. So we could say pair 1 with A, 2 with B, 3 with C. that is a one-to-one correspondence between these two things. Actually, in fact, 1, 2, 3 is going to be in a one-to-one correspondence with any set that has exactly 3 elements. We could also say pair 3 with A, 2 with B, and 1 with C, and that is another one-to-one correspondence. And there are many different ways you could create one-to-one correspondences between two sets that are in one, have at least one, then there are multiple. So being in a one-to-one correspondence is different from being equal sets. So two sets A and B, we call them equivalent if there exists a one-to-one correspondence between the sets. So if two sets are equal, they have exactly the same elements. But if two sets are equivalent, they don't necessarily have the same elements. So equal sets are equivalent, but equivalent sets are not necessarily equal. So that example on the last slide, 1, 2, 3, and ABC, these are equivalent sets, but they are not equal. All right, so if we think about these 4 sets, A is PQRS and B is ABC, C is XYZ, and D is BAC, then compare the sets using the terms equal and equivalent. So the first thing we can say about all of these sets is that each set is going to be both equivalent and equal to itself. So A is equal to A, B is equal to B, C is equal to C, D is equal to D, and A is equivalent to A, B is equivalent to B, C is equivalent to C, and D is equivalent to D. So off the bat, we can always say that about a set in itself. So if we think about A and B, A has 4 elements and B has 3. So these sets are neither equivalent nor equal. There's no way to make a one-to-one correspondence between the two, and they have very distinct elements, P, Q, R, S, and ABC. They don't even have any in common. So if we think about A and C, A and C are in the same boat, right? They are not equivalent and not equal. And again, they don't even have any overlap. But if we think about A and D, same story. They're not equivalent, not equal. Finally, if we think about B and C, these are going to be equivalent but not equal. So these are equivalent because we can make a one-to-one correspondence between them, right? We could say A gets paired with X, B gets paired with Y, C gets paired with Z. That's a one-to-one correspondence. But they're not equal sets because they don't have the same elements. A, B, and C are different elements than X, Y, and Z. But finally, if we think about B and D are actually equal because they both contain A, they both contain B, they both contain C, and neither contains anything else. So B and D are equivalent and equal. And since C was equivalent but not equal to B, it's also equivalent but not equal to D because D and B are the same. They're equal. All right, so moving on to another set of definition for sets, we have cardinal numbers, or cardinality is what we use to describe the number of elements in a set. So in parentheses S tells us the cardinal number of a set S, or the number of elements in that set. So we can figure out the cardinality of each of these sets. So K is the set of 3, 5, 8, 0, 11. So that's 5 elements. So the cardinality of the set K is 5. L is the set containing 0. So 0 is 1 element. So L has a cardinality of 1. So X is the set of all numbers that are real numbers, and X equals X plus 1. So there are actually no numbers that this is true for. So there are no numbers, no real numbers where X is equal to X plus 1. That would be like saying 4 is equal to 4 plus 1, or 4.5 is equal to 4.5 plus 1. So there are no elements in this set. So the cardinality of the set X is 0, since there are 0 elements in it. And then lastly, Y, we use this kind of a circle with a slash through it to indicate the empty set. So that means that it is the set with nothing in it. and it also has a cardinality of 0. We have finite sets versus infinite sets. So a set is finite if its cardinality is 0, so the empty set, or a natural number. So we could pair some natural number to describe the cardinality of the set. So examples, set of presidents in the United States, the set of planets in our solar system, those are both finite sets. And intuitively, an infinite set is just a set that's not finite. So examples of this would be the whole numbers. So starting our counting at 0 and we go up forever. We can never find a natural number that would describe the size of that set. We also have the set of solutions to the equation x plus 1 equals x plus 1. There are infinitely many values we could put in for x for that equation to be true. All right, so the universal set, or the universe, we usually use the letter U, capital U, to describe it, is the set of all the elements that are being considered in a given discussion. So, for example, we could have the universal set being the set X, such that X is a member of the United States Senate. So if we want to use some visual representation for sets, we can use a Venn diagram, and the universal set is denoted with a large rectangle, and then particular sets are indicated with geometric figures inside of the rectangle, usually ovals or circles. In this case, only members of the US Senate are included in the rectangle. This is a Venn diagram. So we could have our Venn diagram here. So me, Dr. Heath, is not a US Senator. So I would not even be in this universal set. I'm not part of the discussion when we talk about the set of United States Senators. But if we think about the members of the universal set who are females, this set is wholly contained in U in the universal set, but does not contain all the members of U. We denote this set with a circle as follows. So we can draw the circle F of the set F to represent all of the female US senators, and everyone outside of that circle would be the non-female US senators. So speaking of not female US senators, we would have the complement of that set. So considering the members of the universal set U who are not females, this is the set of all members not in F, but are in U. They're still in the universal set. So this wouldn't include, I don't know, this wouldn't include Kobe Bryant. He is not, even though he's not female, he's not a US Senator. So he would not be included in this complement. It would only be the members of the set of US Senators who are not female. We can write the complement of a set with this bar over the top. So A complement is A with this bar over it. So it's all the members of the universal set that are not in A. So X such that X is in the U, the universal set, and not in A. All right, so the set B is a subset of the set A, and we write this with this kind of curved, long, elongated C with a line under it, if and only if every element of B is an element of A. So when a set A is not a subset of B, then we can write this with a slash through it. Now, something to note about set equality and subsets is that the definition of subset allows for B to be equal to A. So this underscore here tells us that B is either a subset or equal to A. So this implies B is a subset of A if and only if every element of B is an element of A. And if A is a subset of B and B is a subset of A, then the two sets are equal. So if we want to suppose that set B is a subset of A, but B is not equal to A, then we call that a proper subset. So this would mean that there are things in A that do not belong to B. And we can draw this in a Venn diagram here to show that there are going to be elements in A that are not in B. And we can take away that bar on the bottom of our subset sign if we want to be clear that it is a proper subset. Okay, so if we think about inequalities, we can apply this, use sets to apply this to inequalities. So if we take A and B to be both finite sets, if A and B are equal sets, then their cardinalities will be equal. And A and B are equivalent also because they have the same number of elements, so we can establish a one-to-one correspondence between the two. But if A is a proper subset of B, then we know that everything in A is in B, but there are things in B that aren't in A. So this could be like the 1, 2, 3 and the set 1, 2, 3, 4, right? 4 is in B, but not in A. And so A has 3 elements, B has 4 elements. It's not possible to establish a one-to-one correspondence between A and B if their cardinalities are different from one another. But if A and B are infinite sets, we actually have something else going on here. So if we think about the set of natural numbers compared to the set of whole numbers, they're both infinite sets, and it's clear that the natural numbers are a subset of the whole numbers, right? The whole numbers are all the natural numbers with 0 also. But it is actually still possible to create a one-to-one correspondence between these sets by just mapping every natural number to the whole number 1 smaller than it. So 1 would pair with 0, 2 would pair with 1, 3 pairs with 2, etc. And we can do that forever and ever. So even though N is a subset of W, we don't say that N is smaller than W. They're actually the same size and they're equivalent sets. All right, so that is section 2.2 of your book. I hope this was helpful. As always, let me know if you have any questions, and I hope you have a great day.